Welcome to a new week, and everyone should remember that this Thursday you will have your first mini exam. Last week I also referred to it as test 2, only because that's how it's following in sequence. But based on the information I sent out at the start of our online time, this will be your first mini exam. That content will cover everything through the material we're doing today, section 9.2. So this is still relevant and important for the mini exam on Thursday. We're finishing our chapter 9 today, only looking still at section 9.2 and continuing with discussing how to test hypotheses about two independent samples. But today we're extending that concept to the t-test. So when is this going to come into play? Hopefully you're developing some intuition around this. The two-sample t-test scenario, we still have to assume that we have independence. Independence here means two things. It means that the two samples are obtained in a way that the samples are independent of one another, but each data point that you collect within a sample also has to be independent of every other data point. So theoretically, independence is very important. We'll have an X sample and a Y sample. The X sample, we denote X1 through Xm, and these values are taken IID from a normal population with a mean of mu1 and a variance of sigma 1 squared. And then we have a sample Y1 through Yn, and these are taken IID from a normal population with a mean of mu2 and a variance of sigma 2 squared. Now, in the context of the z-test, the variances were assumed known, at least when we were in normal world. But the t-test arises when the variances are unknown. So we have normality here, but the variances, sigma 1 squared and sigma 2 squared, are now treated as unknown. And you may remember the one sample t-test arose in a similar situation. We had a sample from a normal population, but the variance was not known. So two samples from normal populations, and for each of those, the variance is unknown. So we're still working with the quantity delta, which is the difference of the two means. And our hypothesis of interest is that delta is equal to some specified value delta naught. And of course, the alternative is going to be some kind of negation thereof, whether a partial or a complete negation. Our test statistic is now the t-test, and t observed is given by delta hat minus delta naught over the square root of S1 squared over m plus S2 squared over n. And just to refresh everyone's memories here, delta hat is defined as the difference between the two sample averages, and S1 squared and S2 squared are the sample variances. So that is what goes into the calculation of this test statistic, except for one beast of a calculation, and that is the degrees of freedom. So when we're using a t-test, we need to specify how many degrees of freedom are applicable for the reference distribution. And here, it's rather a tedious calculation to find the degrees of freedom. If you look at this formula for degrees of freedom nu, it depends on the two underlying sample variances as well as the two underlying sample sizes. I'm not going to expect anyone to have this formula memorized, but you should be able to apply it. So we'll definitely look at an example of using this formula tomorrow. But what you'll do is plug in the sample variances, plug in the sample sizes, and whatever value you calculate, you round that down to the nearest integer. And then to evaluate a p-value associated with your test statistic, or even if you're calculating a critical region, you're going to use a t-distribution with new degrees of freedom to do that calculation. Of course, we can also approach this as a confidence interval problem. You're going to calculate the degrees of freedom exactly as on the previous slide. So you still have to use that monstrous formula. But then your confidence interval is given by delta hat plus or minus t-value with area alpha over 2 to the right, new degrees of freedom, multiplied by square root of S1 squared over m plus S2 squared over n. And we will again look at an example of implementing this tomorrow. So at this point, we've looked at something fairly analogous to our last class last week, looking at a situation where we have samples from two normal distributions and the sample variances now are unknown, where last week we treated them as known. And that just steers you towards a t-distribution as opposed to where we used a normal distribution as a reference last week. Now, there is one additional scenario that we're going to consider here. And that is a way to actually simplify things a little bit if we can assume that our samples come from populations with equal variances. So we are still going to assume we have independent samples from normal populations. Variances are still unknown, but in addition to that, we are also assuming that the two populations have equal variances. So we're assuming those population variances, sigma 1 squared and sigma 2 squared, are equal, albeit unknown. We're working under an assumption of unknown variances, but even though they're unknown, we're assuming them to be equal. And when this is the case, it actually simplifies our calculation a little bit in the t-test situation. So it creates an opportunity for us to do what we call pooling of information, which means we can combine the information in a way that gives us a better way of calculating the test statistic. So this requires the additional step of calculating what we call a pooled estimate of variance. We denote that by S subscript P squared, P for pooled in this instance, and the formula for that is a weighted linear combination of your sample variances. So m minus 1 times your first sample variance plus n minus 1 times your second sample variance all over m plus n minus 2. And importantly, this is now the only variance quantity used to calculate the t-observed statistic. So you are no longer going to rely on the two individual sample variances. You're only going to make use of the pooled estimate of variance. So if we're now testing a hypothesis, null hypothesis is still delta equal to some specified value delta naught. alternative is some kind of negation thereof, either complete negation not equal to, or a partial negation, which is directional in some way. And our test statistic, it's still a t statistic, so you're still calculating t observed, but now you're dividing by square root of that pooled estimate of variance times 1 over m plus 1 over n. And where this results in like the biggest headache relief ever is calculation of degrees of freedom, because we can ignore that monstrous formula involving the two sample variances. Degrees of freedom is now simply given by the sum of the two sample sizes minus 2. And still using a t-distribution with new degrees of freedom as a reference, but this, of course, simplified tremendously how we calculate the degrees of freedom. So if you find yourself in this situation, you're going to have two samples, x1 through xm and y1 through yn. So what you need to calculate is x bar and y bar, because this is what you use to calculate your point estimate of the difference of the means. You also need to calculate your sample variances, S1 squared and S2 squared, because that's what you need to calculate your pooled estimate of variance. And this finally lets you calculate t observed and the corresponding p-value or corresponding limit of the critical region, however you are approaching the testing situation. And as always, we can approach this as a confidence interval construction problem rather than a hypothesis testing problem in how we formulate it. So if we have normal distribution and the population variances are equal but unknown, then your confidence interval formula in this instance is given by delta hat plus or minus that t distribution value with area to the right alpha over 2, new degrees of freedom, times the pooled estimate of standard deviation times the square root of 1 over m plus 1 over n, where of course that degrees of freedom is just given by m plus n minus 2. So we are going to look at examples of both of these situations in our live Zoom session tomorrow on Tuesday. But in the meantime, let me know if you have any questions as you are preparing for the exam. I will put up some review questions by this evening for you to also work through. So I will see all of you on Zoom next time that we have a live session.